welcome. We have studied the ratio estimator where we consider the estimate of the population mean YR bar equal to Y bar by X bar into capital X bar. This is ratio estimator because this is the ratio of two sample means we have considered here for estimating the finite population mean. Now, alternatively, we can define another estimator known as the product estimator, which was proposed by M.N. Murthy. In this estimator, as the name suggests, we use the product of two sample means to estimate the population mean. So, the product estimator of the population mean Y bar is given by Yp bar, that is equal to small y bar into small x bar by capital X bar. We use this estimator when the two variables, the study variable y and the auxiliary variable x, are negatively correlated, and this ratio estimator when y and x are positively correlated. So now to define the expected value and the variance of this product estimator, we now consider y bar equal to y bar plus epsilon 1 and x bar equal to x bar plus epsilon 2. So where expectation of epsilon I, this is equal to 0, I equal to 1, 2, and variance of epsilon 1 equal to variance of y bar, that is equal to expectation of epsilon 1 square, that is equal to 1 minus f by n sy square. Similarly, variance of epsilon 2, that is equal to variance of x bar, that is equal to expectation of epsilon 2 square, that is equal to 1 minus f by n sx square. Now, our product estimator is given by Yp bar, that is equal to y bar into x bar divided by x bar. So this will be y bar plus epsilon 1 x bar plus epsilon 2 by x bar. So this will be equal to y bar x bar plus epsilon 1 x bar plus epsilon 2 y bar plus epsilon 1 epsilon 2 divided by x bar. So this is equal to y bar plus epsilon 1 plus r into epsilon 2 plus epsilon 1 epsilon 2 by x bar, where r is the population ratio, that is y bar by x bar. Now, so expectation of the product estimator Yp bar, that is equal to y bar, expectation of epsilon 1 will be 0, r expectation 2, this expectation will be also 0, plus only we have left epsilon 1 epsilon 2 by x bar. So this implies expectation of Yp bar minus y bar equal to expectation of small y bar by capital Y bar, small x bar minus capital X bar. Now this will be equal to 1 minus f by n syx by x bar. So this is the bias of the product estimator. Bias of the product estimator is the expectation of Yp bar minus y bar. So the product estimator is not an unbiased estimator of the population mean, rather it is a biased estimator of the population mean, and its bias is equal to 1 minus f by n SYX by x bar. So now here we can see the bias of the product estimator is 1 minus f by n SYX by x bar. But we know that expectation of the small SYX equal to capital SYX. So this bias can be estimated unbiasedly. Bias of the product estimator can be estimated unbiasedly. So we can correct the product estimator for its bias so that it becomes an unbiased estimator of the population mean. So now we can see bias of the product estimator, that is equal to 1 minus f by n expectation of small yx by x bar. That implies expectation of yp bar equal to y bar plus 1 minus f by n expectation of SYX by x bar. So now we can define another estimator yp bar dash, that is equal to yp bar minus 1 minus f by n SYX by x bar. If you define another estimator like this, so that its expectation will be yp bar dash will be expectation of yp bar. This will be this much minus 1 minus f by n, expectation of SYX will be capital SYX, so its expected value will be 0. So that means this yp bar dash gives an unbiased estimator of the population mean y bar, and this is so yp bar dash is an unbiased estimator of the population mean, and this is obtained by correcting the or by estimating the bias of the product estimator unbiasedly. So now we have the product estimator yp bar equal to y bar plus epsilon 1 plus r epsilon 2 plus epsilon 1 epsilon 2 by x bar. Now this is equal to y bar plus epsilon 1 plus r epsilon 2 plus order of epsilon square. Now this is neglecting this order of epsilon square, this is approximately equal to y bar plus epsilon 1 plus r epsilon 2. Now yp bar minus y bar equal to epsilon 1 plus r epsilon 2, considering up to order of epsilon only and neglecting order of epsilon square, so that if you take the expectation of yp bar minus y bar, that is equal to 0, that is expectation of yp bar equal to y bar. So the product estimator yp bar is an unbiased estimator of the population mean only up to first order of approximation, order of epsilon only. So now we have to obtain the variance of this estimator. Now the variance of yp bar, that is equal to expectation of yp bar minus y bar whole square, expectation of epsilon 1 plus r epsilon 2 whole square, that is equal to expectation of epsilon square plus r square epsilon 2 square plus 2r epsilon 1 epsilon 2. So that is equal to variance of y bar plus r square variance of x bar plus 2r covariance of y bar x bar. So this will be equal to 1 by small n minus 1 by capital N sy square plus r square sx square plus 2r syx. Now this is the variance of the product estimator. Now we shall compare the product estimator with the simple mean comparison with the simple mean estimator y bar. Now we have variance of y bar equal to 1 by small n minus 1 by capital N sy square, and variance of the product estimator, that is equal to 1 by n minus 1 by capital N sy square plus r square sx square plus 2r syx. Now the product estimator yp bar is preferable to simple mean estimator y bar if variance of yp bar is less than variance of y bar. So the product estimator is preferable when to see simple mean estimator when variance of y bar is greater than variance of the product estimator. That implies 1 by small n minus 1 by capital N sy square greater than 1 by n minus 1 by n sy square plus r square sx square plus 2r syx. So that is, we prefer the product estimator when r square sx square plus 2r syx, this is less than 0. So that implies r square r sx square plus 2 rho sy sx is less than 0, because syx by sy sx equal to rho. So syx equal to rho sy into sx. So that implies rho is less than minus r sx by 2sy. So this is the condition when the ratio, the product estimator is preferable to mean per unit estimator. So when we can take r, that is equal to, we have y bar by x bar. So using this, rho is less than by minus sx by x bar divided by 2 sy by y bar. So that implies rho is less than minus 1 by 2 cx by cy, where cx equal to sx by x bar and cy equal to sy by y bar. So under this condition we use product estimator. So if cx equal to cy, that means coefficient of variation between x and coefficient of variation of y, if they are same, then we prefer product estimator if rho less than minus half. From the ratio estimator we have already derived, this is prefer product estimator, and when rho greater than half we prefer a ratio estimator than the mean per unit estimator y bar. So now we have seen that our correlation coefficient lies between -1 to +1. So correlation coefficient between study variable and the auxiliary variable through 0. Now this is -half, this is +half. If rho greater than half, we prefer the ratio estimator YR bar. If rho less than -half, we prefer product estimator YP bar. And in between, when rho rise between -half to +half, we prefer the simple mean estimator Y bar. We never compare between the ratio estimator and the product estimator because they are useful in different context. Ratio estimator is useful when there is a positive correlation, high positive correlation in between the study variable and the auxiliary variable, and the product estimator is used when there is a high negative correlation between study variable and the auxiliary variable. So since both the estimators they are used in different context, so we do not compare between the ratio estimator and the product estimator. Now hope you have enjoyed the video. Thank you.